All right. First of all, thank you all so much for being here. My name is Kevin, and today Montana and I are going to talk to you about machine learning. Now, this may not be the first time that you've heard someone from Google talk about machine learning. We talk about it a lot. In fact, our CEO, Sundar, has gone as far as to say that we will move from a mobile-first world to an AI-first world. But when we talk to developers, the question that we get most often is how to think about machine learning within the context of their business. Sure, they've heard about AlphaGo, or they've used Google Photos, but what about practical ways they can start with machine learning today? Now, we have a diverse audience here today. There's a mix of business people and product managers, designers and developers. Some of you might be experts in machine learning. Others maybe have heard the term, but you're not quite sure where to start or what all the fuss is about. So we're going to break the talk into two parts. Mine will be pretty short. I'm going to give sort of a high-level practical overview of machine learning to make sure that everyone has context for Montana's section. Montana will then share how Instacart uses machine learning in the real-world problems that they're solving using ML. OK, so let's get started. So the first question is, why use machine learning at all? And to answer this, I'd like to give a very simple example. What if I was to ask you to write a program that tells the difference between an apple and an orange? You might start by writing manual rules. For example, maybe you'd count the number of orange pixels in an image versus the number of green pixels and compare the ratio. And that might work for these two images. But the problem with writing manual rules is that it doesn't scale. And for every rule that you come up with, I can find an example that breaks that rule. For instance, what if I gave you an image that was in black and white? Or what if instead of a green apple, I gave you an image of a red apple? Accounting for all of these exceptions and writing all of these rules would require lots and lots of code. And if I gave you a similar problem in the future, like tell me the difference between a raspberry and a strawberry, you'd need to start all over. Clearly, there has to be a better way. Rather than relying on manual rules, machine learning learns from examples. And the general way that a machine learning model works is you take a set of inputs, in this case, labeled images. You feed them into a machine learning model, in this case, a convolutional neural network. And the model makes predictions. And if the predictions are incorrect, what happens is it actually slightly adjusts the model to make it more accurate. Generally, the more data that you put into a machine learning model, the more accurate it will be. What this allows you to do is then you can take a new set of data that's totally unlabeled, feed it into a machine learning model, and the model will tell you either that this is an orange or an apple. Now, I'm simplifying a little bit here. Montana, please don't kill me. But in general, when you think of the workflow for machine learning, there are really three steps that you need to follow. The first is to collect data. So what does data mean? Data comes in different forms. Data can be images or audio. It can be numbers in a database or a spreadsheet. It can be structured or it can be unstructured. The data collection step specifically, by that I mean quantity of data, quality of data, maybe which features you choose to include in your model, is often the most challenging step to getting started with machine learning. When we talk to developers, this is the biggest obstacle that they have to overcome. And Montana's going to talk about this a little bit more in a minute. The second step is you need to choose your model. Models come in different flavors, too. There are deep learning models and shallow learning models. There are pre-built models or models that you can build on your own. There are models that need labeled data and those that don't. This is often a step that I think developers that are new to machine learning are most intimidated by. But the truth is, for most common machine learning tasks, there are open source models that you can use. So when you choose a model, what should you think about? The first thing is, what problem are you trying to solve? There are different ML models for different problems. The second is, what data do you have at your disposal? And then the third is, what other considerations do you have? For example, are there latency requirements where you might need to use on-device machine learning? Or are there compute restrictions? The last step is to predict and tune. Now, tuning really depends on your level of sophistication. If you're new to machine learning, like I said, there are plenty of models you can use that don't require any tuning at all. But if you're more sophisticated, there are things you can do to tweak a model and make it more accurate. OK, so that's great. What about real-world use cases? What problems can machine learning actually solve? So I put together some use cases that I think are broadly applicable to folks in this room. This is not a comprehensive list. The beauty of machine learning really is that it can solve many, many different types of problems. I should also caveat this by saying that in some cases, you can solve some of these problems in multiple ways. But one framework that you can use when thinking about what problems you can solve for your specific business is to start with what kind of data is available. If you have high-quality labeled data, you can do something called supervised learning. And supervised learning kind of has two buckets. The first is classification, right? Identify an image. The second is regression. For the game developers in the room, maybe forecasting LTV or predicting the likelihood that a given transaction is fraudulent. Even if you don't have high-quality labeled data, you can still conduct what we call unsupervised learning tasks. This is essentially where the model will infer patterns or commonalities in data. And you can use clustering or association models to do things like segment your customers or determine which product you want to cross-sell at the time of purchase. So I'm not going to spend too much more time here. Montana has some really great examples that he's going to share in about a minute. And it's easy to get started. Like I said, there are plenty of pre-trained and off-the-shelf models you can use using the Google Cloud Machine Learning API, things like vision, speech, translation, and natural language. I'd also encourage everyone to check out Tensorflow. Tensorflow is the best-in-class and most popular open-source machine learning library. It's the same code that we use internally for most of our projects internally at Google. Finally, since this is a mobile audience, I wanted to let you know that we're making mobile-specific investments as well. So 3 quick plugs. The first is that with MR1, which is coming later this year, we'll be announcing the neural nets API, which enables hardware acceleration on the device. The second is TensorFlow Lite, something that we announced at Google I/O this year. We're also hoping to launch before the end of the year. TensorFlow Lite is essentially TensorFlow that's optimized for smartphone runtimes. And then third, we're working on a set of top-level APIs that make common machine learning tasks easier. I'd also like to say, if anyone is thinking about machine learning at all, we have Brahim, who's our PM for machine learning at Android, as well as a number of our engineers that are going to be in the classroom later. Please go find them. They'd love to hear about what problems you're trying to solve and answer any questions that you have. OK, so with that, I'd like to introduce Montana, who's going to talk about how Instacart uses machine learning.
Thanks, Kevin. So I'm always impressed when somebody can summarize a very complex topic in 3 easy steps. My artistic friend did one better when I asked them, how do you draw an owl? Well, they said, first, you start off with a circle, and add another circle, and this is sort of the head and the body, and then you just draw the damn owl. I'm going to try and break this down, those 3 steps, into quite a few more as we go through several high-level overviews of when we use supervised learning at Instacart, when we use unsupervised learning. And at the end of the talk, we'll go through a detailed feature development use case, and we'll talk about how we start and how we finish. To begin, I'd like to give you some context of what Instacart is, how our business works, so that you understand why we would use machine learning to solve any problem we have. We deliver groceries from the stores you love in as little as an hour. We connect personal shoppers to our customers so that they can deliver the service those customers expect in real time. We also partner with hundreds of retailers around the country so that we can shop out of their stores, we can provide discount prices. That way we have deep integrations with their product catalogs we host on our website. The fourth party in this marketplace are the actual product manufacturers. We partner with them to give our customers discounts, coupons, and other incentives on the website. So at the heart of this is a ton of data passing back and forth between a lot of parties. And what really drives this engine in terms of growth and efficiency are deep machine learning models. I'm going to walk you through the customer experience to begin. When they get to the app, they choose a store. They shop for their groceries. They go ahead and check out in the app. We have all their payment information saved, so it's real easy. They select a delivery time that's convenient for them. And after that, we've got it in the bag. I promise that's the only pun in this talk. I think. On the other side of the transaction, there's a shopper. The shopper lets us know when they're available to do work. They'll acknowledge an order as it comes in. They'll go pick all of the groceries for that customer. We make sure that they scan every item for accuracy. This is actually a step that improves their speed because it's easier for your phone to tell you yes or no when you're trying to decide 2%, 1%, light, whole, all the labels look the same. So this is a nice improvement. And then the shopper actually delivers it to the customer's address. We don't discriminate between cats and dogs. We're an equal pet service. So I'd like to show you an example of one of our teams that uses machine learning pretty extensively. It's our search and discovery team, which powers our storefront that all of our customers use. If you think about search when you're dealing with a product catalog, very minor changes in search terms should have completely different results page. What you see on a milk results page should be completely different than a chocolate milk results page and should be completely different than a milk chocolate results page. That's hard if you're just using text. So one reason we use machine learning is to extract more meaning and provide more relevant results. The beginning of any machine learning problem is to break down all of your input into specific features. In this case, the features of all of our products are, is it USDA? Is it organic? What's the fat content? What's the size of the container? What's the color of the image? All of these become features of products. And so we don't really think of products as an ID or name, but they're a huge collection of potentially dozens or more of these features. And the important thing about all of these features is that they can be quantified numerically. For color, we can assign red, green, blue numbers. Machine learning models only work with numbers. Fundamentally, they're arithmetic all the way down. So if we can quantify milk in a series of features that are embedded as numbers in our models, then we can actually apply really advanced mathematics to get better search results. So the way that we actually translate a search ranking problem into a supervised machine learning problem is we use the signal of when a user adds a search result to their cart. If they actually decide to buy something that we show them when they search for milk, that's a supervisor saying this is the correct search result. There's also an implicit negative signal there of everything else we showed them on that page isn't quite as milky to them. So doing this with libraries like Tensorflow that Kevin pointed out, we can really improve the situation. And what's even cooler is that as we launch new retailers and add hundreds of new products to our catalog every single day, we can identify what new products will also be highly ranked search results immediately, because we look at these products in terms of their features, not in terms of any individual product's history. So the fact that this product has similar features to other things that have ranked highly for milk means this product should probably rank highly for milk as well. Once you've built one machine learning model and you've got your data in a good shape, then you can start to think about all of the other signals you have. One of the superpowers of deep learning is called transfer learning. You can take the understanding that one model has developed, in this case our search results model. It understands that these particular features are closely related to the term milk. Or in this case, these two sets of features, the ones that represent Coca-Cola and Pepsi, are closely related to the term cola. In terms of their features, they're very similar. We could subtract them and get 0 in mathematical sense. But what we see when we have Coca-Cola and Pepsi is that people almost never add them to the cart at the same time. So this is another signal that even though these two products have incredibly similar features, they're never added to the cart at the same time, making them competitive. So now we can start merchandising all of our website. And when people are looking at Coke, they should also see Pepsi. When people are looking at all of these different types of items that are similar. We can take another signal, very similar, but it's the opposite. In this case, peanut butter and jelly are often added to the cart at the same time, but they have very dissimilar features. So using this knowledge we have now about what features are similar and how they work, we can recommend products. After we see you add peanut butter to your cart, then we can say, hey, you probably are forgetting the jelly. And that's a different application than organizing our storefront in the beginning. All of this requires that we collect the data from the user acting as a supervisor for our machine learning algorithms that are continuously running and taking in new data over time. I'd like to move on to an example of unsupervised learning that Kevin mentioned. It's called clustering. In this case, we don't necessarily start with the answers. We don't have somebody training our algorithm with the correct answer. We start with questions. We want to know more about who our users are, what they want, what motivates them. Some people in the past would use demographic data to understand their user base, but that's sort of irrelevant in many cases. It doesn't really matter, how old you are, or what sex you are, or what age you are, when you're talking about behavior-driven development. What we want to do is we want to actually segment our users, not by these superficial qualities, but instead by how they actually use the app and derive value from it. It starts just the same way. We break our users down into a set of features. It might be what platform are they visiting the site on, what time of day do they come to the site. A funny one is AOL.com email addresses are significantly different than Gmail.com email addresses. Those users tend to engage with the site differently at different times of the day. And so even at sign-up time, we know a lot about a user and how they're going to behave. We can use an unsupervised learning model to begin to cluster these users. And so it will actually begin to pull out groups of these people. In this case, I've asked for 3 groups and that's the only parameter I specify for the model, because I want to maybe make a small, a medium, and a large version of my product. And I want to decide what should those 3 versions of my product be. In this case, we've got group 1, which are green people, group 2, which are orange people, and group 3, which are blue people. To begin with, the unsupervised model has just told me that blue people are very much like blue people, orange people are very much like orange people, and green people are very much like green people. But that doesn't really help me too much. What I need to then do is do some deep analysis on the green people versus the orange people versus the blue people versus our normal overall global user base. And what I might find is that green people tend to prefer organic food. Orange people tend to prefer spicy food. And blue people really love ice cream late at night with a frozen pizza. So that's one way that we can use machine learning to plan how we're going to build products that people are going to engage with, even before we launch. I'd like to go through a detailed sort of analysis on what our product development looks like. This is a case for picking groceries. We do a lot of picking groceries. It's sort of where a huge portion of time goes. We have this enormous catalog that shoppers are handed in a single shopping list. They go out to all these different stores that they may never have been to before, and eventually they will complete the order. If we can save 10 seconds, 20 seconds per order, at scale, this becomes hugely valuable to the company. So we've looked at lots of ways to improve their speed. I mentioned the barcode scanner was one incidental metric. But when we do these things at scale, it becomes very difficult. We have hundreds of different retailers that we partner with, millions of products, thousands of stores. Actually organizing the data on how every single store is laid out is incredibly challenging. So, we go to our CEO after he says speed up picking. I said, well, if we could just be like some of our competitors, why don't we just build our warehouses, and then we'll know where everything is, and we can have robots do this, and it'll be super fast. Porva said no. That's not our business model. We don't build warehouses. We shop out of stores people like. So we said, okay, well, maybe we can get more data about each individual store. And maybe we can sort the shopping lists that way, and we can speed up shopping time. So we do a little weekend hackathon project, and it's a little Rails app that lets us sort of take where baby accessories are and put them on an aisle number in the store, and then some shift lead in a store can drag and drop all of our categories in order. They can say aisle 15 comes after aisle 14, after aisle 13, and then when we ship a shopping list this way, we can put things in the order that has been specified at that store. This is our baseline control where we started. If you notice, it goes up and to the right, which is generally good. In this case, what that means is as we add more items to the order, the individual time per item goes down. So it's an improvement. That if you're shopping for 10 items in a store, you have to walk around the whole store to only get 10 items. If you're shopping for 50 items in a store, you walk around the whole store still only one time, but now you've got 50 items. So we've known for a long time that this is a key to our business. What we haven't known is if we can change the shape of this curve. When we launched that experiment, we actually showed that there's a significant slope improvement. We're very excited. Unfortunately, this is too expensive. Our CEO says this works in one store. That's great. But next week, when they move everything around again, we're going to have to go do this over again. And by the way, we're growing insanely fast, so I can't see us sparing the labor hours to do this. So we say, OK, fine, Apoorva. Maybe there's something smarter we can do. We have phones with GPS on them. Shoppers are in these stores 8 hours a day. They're picking hundreds of times a day. Maybe we can actually sort of map implicitly using GPS. We know the time they pick the item because they're scanning it with the barcode. We know relatively where they are in the store with GPS. If we see enough picks on that product, over time we can start to map the whole store. And we can start to build up a detailed analysis of where the baby diapers are in this store. Once we have a map like this, for any given order, we can plop the dots on the map. We can solve the traveling salesman problem. We can actually solve it for small orders. We use heuristic approximations for large orders. And the results for that were exciting, but disappointing, because we actually saw a significant improvement over baseline, and now we're not paying anybody to do this. Now this is implicit data that we get for free. It's just an algorithm running. But we know that it's not really as good as what the humans were able to do. There's some deficiencies in this algorithm that it doesn't know where walls are. So it might ask you to walk through an aisle. And so we weren't quite ready to stop there. We started looking around for, is there tech that will give us more accurate mapping information? We're really excited about things like Google Tango coming out. A lot of this AR is going to be big for us. It's going to really change the way we do things. But it's not really ubiquitous yet, so we can't expect all of our shoppers to go buy brand new devices to shop with us. Once we've exhausted all of the options, what do? We kind of smear some machine learning on the problem and see what happens. So in any machine learning problem, you need a formal problem statement. We like to do our problem statements in emoji. In this case, you have 10 products, some corn to coffee. And the goal of this machine learning algorithm is to put those products in the correct sequence. So that then we can predict this sequence. For a specific instance, stated mathematically, the probability that the next item is going to be the cookie, given that the last item is bread, and your candidates are the items that remain to be shopped, is the function that we're trying to learn with the machine learning model. We use a Tensorflow architecture to build this machine learning model. In this case, you can see that our model actually takes features from several different things. It considers what the features of the shopper that's shopping is, how experienced are they, how long have they been on shift, how many refunds do they typically do during an order, how quickly do they typically shop an order. It looks at the warehouse location that they're at, so that it can say, how big is this place, how confusingly is it laid out, do they typically have things that are out of stock that they haven't told us about. It looks at the previous item that they just picked, which in this case is bread, and it looks at the next item that they might pick. One really important thing that I touched on earlier is this notion of embeddings. When you have features for a product that are numerically represented. The model, as it's incrementally updated, it embeds that set of features into itself. And so in this case, we actually have two products that are coming into this model as features. TensorFlow lets us share that embedding, so the model only has to learn about products one time, which doubles the efficiency. The goal of this model is to actually make a prediction of whether the chocolate bar will be the next item picked, given that bread was the previous item picked. They're at this retailer with this shopper. With enough examples, we can actually train this model and learn this function. We're going to call this thing, this model that we've just trained, the score generator. And we're going to set it up the top right-hand corner for now and go a little bit deeper in how we use this score generator to actually sequence an order. We generate a score for every product, given the input features. And then we do that for every remaining product inside the availability set. You can see that it's going to predict several different scores. Some things are very probable to be picked next. Some things are less probable to be picked next. We take the most likely one of that. Softmax is a fancy mathematical term for that. We get a prediction, and we actually use cross-entropy, which is a way to teach the model that these answers are constrained to the available ones you're looking at now. There are millions of other products in our catalog. I don't know if you're familiar with Silicon Valley, if anybody watches that. The hot dog, no hot dog machine learning classifier, he couldn't actually make it universal. He couldn't train it so that it can actually do more than one thing. Our classifier actually can consider all things because it's a single model that represents all stores, all products, confined to the very small list of available products remaining in your shopping list. That's the cross-entropy function, gives us that little extra nudge. And so given that model, we can now actually make predictions every step of the way that corn will be the most likely item picked first. Given that they've just picked corn, what will be the next item that they picked with all the rest of these? We repeat that until we've actually exhausted the entire list of available products. And then we can show that to the shoppers. So the question is, this sounds really complicated. Does it actually work? And the answer is smashingly. We're very, very excited with the results here. To give you an idea, if there are 125 million households in the US, if 5% of them do business on Instacart, they typically shop for groceries about once a week. If we can save about a minute a week, then that's 618 years of labor that we save every single week with a model like this. Once we have a model in production like this, it's really easy to tweak it, to add more features, to see which ones make sense, which ones are harming the model's performance, to add extra hidden layers. We went through about 7 iterations on this one, and we actually doubled the performance of it compared to the baseline. So we're at over 1 millennia saved per week now, which we're very happy about. So that's all I've got. I'm going to turn it back over to Kevin, who should be able to give us some closing notes before lunch.